This is a joint work with Professor David Perry. We studied discrete time MM1 type vacation queues with catastrophes through two-colored weighted lattice paths. I will present the main construction and the results we obtain from it. A regenerative decomposition, explicit basis cycle generating function, exact coefficient information asymptotic, and extension with catastrophes and Motzkin paths. Okay. Okay, let me start from the roadmap. First, we define the queuing model, vacation, walking mode, and catastrophes. Then we translate the model into a two-colored weighted path. The central idea is a regeneration at level 0. And the main result is a busy cycle generating function. We will see the proof sketch. We will use first passage kernel root and geometric sum manipulation. Then we state coefficient and asymptotic consequences and explain how catastrophes and Motzkin paths fit into the same framework. Okay, a bit about Q theory. Our Q has two operating regimes, vacation and walking. It is a simple one, MM1 type memoryless Poisson arrivals and exponential service time. And our system has only one server and two regimes. In vacation mode, customers may arrive, but no one is served. No one. In walking mode, arrivals and service completion may both occur. There is also a catastrophe, disaster event. From any positive level, the system jumps directly to 0. If we observe a queue only at state-changing event epochs, its evolution is naturally represented by a two-colored dig-type path. We will see it in the next presentation. If instead we observe a system on a uniform time grid, some time steps leave the state unchanged, and this leads naturally to two-colored Motzkin type path. Okay, now I want to present you video simulation and explain how our model works and how it related to lattice paths. So just a moment. Sure. Let me check. Yes. Oh. So let's start it. Start the simulation, and I will explain and comment how the system works. This is the Q model, and this is the lattice path. So let's restart it, and let's start. Okay. To Q or not to Q? This is always a question. Yes, to be or not to be. Let me show the queuing model behind our combinatorial construction. We have here one server, now it's on vacation, and two operating regimes. The service starts in vacation mode, shown in blue. Customers may arrive, but not service take place. Here comes the first customer. The queue length becomes 1 when the second customer arrives, and the third one. Where is it? Where is here? Okay, we'll need to wait here. So during vacation, the queue can grow. At some random time, we need to wait. Vacation ends. Notice the important point. The queue level does not change. We had 3 customers before the transition, and we still have 3 afterwards. Only the operating regime changed from the vacation to walking. Is from red to blue. Now the server is walking. Server completion move queue down, but customers may still arrive during the walking period. Also pay attention to lattice path. Okay, additional customers arrived. Okay. We need to wait until the last customer is served and the system returns to 0. This point will be important. 0 is a natural regeneration point of the process. Okay. Now, a new vacation cycle starts. A customer arrives, Another one arrives. Okay, we need to wait. With one possible event, a catastrophe, disaster. It can occur in either regime and sends the system directly to zero. The lattice path here below records the evolution of the queue length. On the next slide, we will translate this evolution into two-colored weight lattice path. Okay, so this is a process. This is queue process, and this is the appropriated lattice path, two-colored lattice path. Okay, so let's return to the slides. Now let's formalize what the video showed. Each queuing event becomes a colored step. Arrivals are up steps, and service completion are down steps. Vacation arrivals are blue, walk-in events are red. The same queue level belongs to two different operating regimes, so the color is also part of the state. Pay attention, each step also carries a weight. It can be probability determined by the model. For example, PB, PR, QR, it's a steps that we can define from the probability model, from the appropriated queuing model. The weight of the whole path is the product of the weights of its steps. So weighted paths give us the bridge from queuing to combinatoric model. Okay, let's define what we want to count. We denote by F3 Zx the generating function of all weighted paths, now without catastrophes. We will add them afterward. So the Z counts the number of steps, and X records the final queue level. So the coefficient of Z to power n x power m in F3 give us the total weight of all paths with n steps ending at level n. We need additional notion of busy cycle. Busy cycle starts at level 0 and ends at the first return to 0. And now we want to introduce two objects. Use the regeneration. B of Z and U of Z. B of Z counts the completed busy cycles, and U of Z and X count the unfinished final tail of cycle. For the next result, catastrophes, as I said previously, we don't use it when turned off. We don't have a catastrophes. Okay. So the return to 0, first return to 0, give us the regeneration structure of the process. Every time the path return to 0, one busy cycle is completed. After the last completed busy cycle, the path may either stop at 0 or continue with one unfinished final tail. Here we will use U. We include the empty tail in U of Z and X. Though a full catastrophe-free path consists of 0 or more busy cycles and one final tail. And here we get this first equality. F3Zx equals to this value. Okay, this is geometric series, so we get this result. F3 equals U over 1 minus B. You can ask me where is catastrophe, we'll talk about it in the next slides. So this is the first result. To compute B of Z, we can isolate the rate first passage descent. Let H of Z count the red paths from level 1 to level 0 with the first hit of 0 at the final step. Here we use kernel method to find H of Z, but first of all, we can find the kernel method identified H with the power series root of x1, and this fellow is very similar. It's very similar to Catalan numbers, but we need to use here the appropriate weights of the edges. So this is x1, and hz equals x1 at point z. Here the main explicit form. B of Z. As we said previously, B of Z counts basis cycles in the catastrophe-free core. The theorem gives that B of Z equals gamma square of Z x1 divided by 1 minus PB. It's a weight over each Z x1, where x1 is a red first passage generating function. So this compact formula encodes the busy cycle length distribution. Okay. Why this theorem is correct? I only want to give a sketch. Red first passage gives a quadratic equation for H. It's 1, similar to Catalan. And its solution xx1. Now we fix the switch level M, and such path, a busy cycle, is built from blue buildup, one switch from vacation to working period, and red first passage descent. So we get this expression for BZ. Okay. Using the asymptotic analysis from analytic combinatorics, we can find analytical expression for BZ in different situations. I need to skip it on because I don't have enough time. But here we can asymptotic analysis of B representation of Bn. Now, the last step, I want to demonstrate a catastrophes. A catastrophe is one step change, time it change by 1, and level jumps directly to 0. The useful point, we can extend our model. Using catastrophe, we found calculating and found expression for generating function from the start. Let A of Z count one catastrophe block. It has the next form, a catastrophe-free path to some positive level, followed by one catastrophe back to 0. Let DZ count a number of such blocks. When by geometric linear factor, we get that DZ is equals 1 plus AZ plus square of AZ, and so on. So DZ is a geometric series. And now we have final expression for generating function of model with catastrophes. It equals DZ, any number of catastrophe paths, times F3 ZX. This is expression for the path without catastrophe. And this is the final expression. Okay, using this generating function, we can find many interesting quantities of interest, both in Q theory and combinatorical analysis. We can find busy cycle length distribution, expected busy cycle length, exact coefficient, asymptotic regimes, and so on. One thing I want to add, here I describe the dig path. And dig paths describe state changing event epochs. If we want to extend this model, the Motzkin path appears when we add uniformized times quanta. In some epochs in Q system, the state of the system is not changed. And here we can use horizontal steps, similarly in Motzkin path. So we can extend this model to Motzkin paths and continue to analyze it using the Motzkin. Okay, thank you all. Thank you.